A little bit specific, really to the case of groups of Lie type. I'll try to explain how this theory of the linguistic that Meinhof talked about, which was used to understand the complex irreducible characters, fits together with the block theory and the possible existence of basic sets of characters. Okay, so we'll start with G, a connected reductive group. Which will be defined over some finite field. So the way to define the structure is to fix a Frobenius endomorphism. Yes, and the finite group of Lie type will be this GF. Okay, so the way you construct the representation is really from the geometry. So you have given any stable maximal torus, which is included in some Borel subgroup, not necessarily F stable. You can associate some variety, algebraic variety, which was denoted by Y in Meinhof-Stokes. And this variety is endowed with two actions, one of the group G on the left, one of the finite torus on the right. And you should see this as really like a biset. So instead of a biset, it's really an algebraic variety, but you have these two actions. So if you consider the permutation module associated to the set, you will have a bimodule. But here, since you're working with an algebraic variety, the way you linearize things is by taking some suitable cohomology. So you can construct, you can look at the cohomology groups of this variety over, so it could be QL bar. But from the setting that I started from, I had fixed some L modular system. K, O, and small k. This one being some finite extension of QL. Okay, so I can, instead of working with QL bar, I can work with coefficient in K. And this is now really a bimodule for these two actions. Okay, and you can construct, given any irreducible, or not even necessarily irreducible representation of the torus, over K, so really an ordinary character, a complex character if you want. You can construct some virtual character this time. So you look at each cohomology group of your variety. You cut by the action of theta, so you keep only the isotypic part, the theta isotypic part, so only the part where your torus acts via this character theta. And you take the alternating sum, and what you get is an element, so a virtual character, so an element of the Grothendieck group of your presentations. Okay, you can think of it as a central function or as a linear combination of character, but with possible non-positive coefficients here. Okay, so that's for the characteristic zero, and there are, two really important properties of these characters is the linguistic characters. The first one is that they're really helpful in the sense that every irreducible character will occur in some linguistic character. So I should say, we call this generation. I'm not sure that's the correct word, but by this I mean that every irreducible character of GF. So by this really I mean a complex character, so an element of this set occurs in some RTG of theta. So for a pair T and theta, so T being some f-stable maximal torus, theta some irreducible character of the finite torus. So that's one property, but you can also tell when two de-linguistic characters will have a common constituent. So let's say that's a result about the disjointness of these characters, of the constituent of these characters, is that if you have a character chi occurs in different RTG theta, is such that chi is a constituent of RTG of theta, but also of some other de-linguistic characters, so for different torus, and for different character of the finite torus, the corresponding finite torus. So this is, if this is non-zero, then you can describe explicitly the relation between the pair T theta and the pair T theta prime. Okay, so I won't say exactly what it is. So I will write it like this as a conjugation. And we say that the pairs here are geometrically conjugate. Okay, so there is a notion of conjugation. So for torus, that's the usual notion. But when you conjugate, so you know that there is a single conjugacy class of maximal tori. So T prime is always conjugate to T. But then since you're working with characters of the corresponding finite group, if you take the conjugation by an element which is not in the finite group, then you don't have a character of the finite group. So there is a specific conjugation that you have to define in order to understand how to pass from a character of T prime to a character of, the finite group corresponding to T. Okay, but this is very explicit, and you can make it very simple if you go to the Lagrange dual and working with conjugacy classes of semi-simple elements, which I won't do, it will become too technical otherwise. But just to mention that there is really a way to partition the set of characters into which conjugacy class of pair it occurs. That's really the graph that Meinolf mentioned before. So if you're really living in separate conjugacy classes, you're living very in different worlds in terms of characters in characteristic zero. Okay? And the question that I want to address today is what's the equivalent, what's the analog over the field of positive characteristics? So K is really this field of characteristic R. All right, so let me just mention something probably as an example, even if I don't want to spend too much time on this conjugacy class. Let me just say that if you take all, so every, there is one character which is common to every finite torus, it's the trivial character. Okay. So if you look at all the pairs where T varies among the f-stable maximal torus, then this is a single conjugacy class. So orbit, I would say, conjugacy class. And all the constituents of the linguistic character attached to these ones are exactly the ones which are called the unipotent characters. Okay, so that's specific cases. You have other series like this, but somehow the most important one, if you're able to understand this one, then there is a good chance that you can understand the others. All right. So let me say something about the analog. So in order to do that, I have first to explain since these characters, they're really constructed from characters of the tori. So here, before giving any property on these linguistic characters, I have to tell you what happens for this group, this finite abelian group TF, when you pass from characteristic 0 to characteristic L. Okay, so this will be somehow an example which sits in the middle of the both, of the extreme cases that I mentioned last time, the L group and the L prime group. And that's quite instructive for understanding the sequel. So what happens for this abelian group? So if you start with T, some maximal torus, or any torus, F stable, this is an abelian group, finite abelian group. So what can you do in that case? You can, since we're going to work in characteristic L, you can separate the elements whose order are powers of L of the elements whose order are prime to L. So you can write it this way, T L prime times TL. So this is just a set of L prime elements, which is a group in this case because we're working with abelian groups. And this is a set of L elements, okay? So here you really have some L prime group whose representation theory will be easy, going from characteristic 0 to characteristic L. And this one is, it's easy but in a completely different way. By this I mean that like the group algebra would be just a single block. Okay, so let me, probably explain this. If I start with the ring O, I can decompose. I have a similar decomposition for the group algebra in terms of the group algebra of this L prime group tensored with the group algebra of this L group. So this one, you've seen in Rada's talk that this is indecomposable, and you have only one representation in positive characteristic with only one irreducible representation over K, which is just a trivial representation, okay? So you should think it just, this is, as a representation, it's just a projective cover of that representation over O. And this one is the opposite, is that it will decompose as just a direct sum of one-dimensional representation, okay? But also as an algebra. So since I'm working again with like an abelian group, every representation has dimension 1, every irreducible one has dimension 1, which means that the block decomposition of this one would just be like a decomposition of lines like this. Okay, so let me be more precise about this one. So if I start from a character in characteristic 0 of the torus, what I can do is restrict it to a character of this subgroup. So the restriction to TL prime. Okay, so this is now an irreducible character of TL prime. Okay, and I can, so that will correspond to summand of this decomposition. And one way to single out that summand is to take the idempotent corresponding to the character, which will be exactly, in that case, the block idempotent corresponding to this semi-simple algebra. Okay, so you can consider E theta. So maybe let's say directly, you can define an idempotent of the whole algebra by, so let's call it B theta. So you take, on that side, use this decomposition. On that side, you take the idempotent corresponding to theta, to the block corresponding to restriction of theta. And on this one, you don't have the choice. It's indecomposable, so you just take the unit. So E theta restricted to EL prime times 1. And what is explicitly what it is? Well, it's just writing this one. So you have to divide by the order of T prime L, and then you sum over all the elements of TL prime. You apply, let's do it this way. Look at this element. And because we're working with an L prime group here, this is really an element of OTF. You can check that it's an idempotent, that it's central. This is the one that will give you the block, okay? So this is the block idempotent, and you can see from that definition is that what really matters is not the character theta itself, but really its restriction to L prime, okay? So the irreducible character that you will get in this block, okay, so by definition, that will be the characters lying in the block corresponding to this idempotence. So B theta K let's see, OTF. By definition, what are there? I mean, if you change the definition, like I say, if you don't remove, I mean, if you don't change this restriction, you don't change the idempotence, so you will still be in the same block. So you end up with all the characters of the torus which have the same restriction. Okay, so let me write it. Theta restricted to TL prime. That's the same. Okay? But there is another way to say it. In terms of the decomposition map. It will be the characters of the torus which have the same decomposition as theta. Okay. If you start, I mean, if you have this abelian group and a character of dimension 1, a linear character, what happens really when you pass modulo L is that all the L root of unity, they become 1. So what really matters is just a restriction to this L prime elements, so just a restriction to this group. Okay, so it's exactly equivalent, having this equality and this one. Sorry? So D is the decomposition map. So here, so D should be thought as the map from the Grothendieck group of the characters of TF, so over K, to the representation in positive characteristic. Okay, but this is really, I mean, this is really the group generated by somehow the characters of TL prime. Okay, in that case, in that setting. Okay, but what's important to notice is that really you get like every character which have the same restriction to TL prime will be in the same block. And from, I mean, and in this one, in this set, there is one really you can single out because we're really looking for basic sets. Okay, so we want a subset of characters which will parameterize the set of modular representation. But here, among all the characters which have the same restriction to TL prime, there is one which is a bit different from the others, is the one which is trivial on the L prime, on the L part. Okay, so there is in this block, there is a unique character theta, such that now when you restrict to the second summand, to TL, this is the trivial representation, trivial character. Okay, so I'm saying modulo L, that restriction doesn't matter. You don't see it when you restrict here, when you take the decomposition map. But still, if you lift everything up to the characteristic 0, it will matter which one you take. And I mean, for simplicity, we would like to take the one which is trivial on this L group. Okay, and that gives you a basic set. Which would be just the set of character of TF, such that the restriction is 1. Okay, so that's a basic set for for TF, for the whole group. Okay, so that's for the tori, and what's going to happen for the linguistic character would be exactly the case. They get exactly the same thing, except that you have, to apply this strange operation, this strange induction RTG. That will be exactly what will happen. The price to pay is that you will not obtain just blocks, but really unions of blocks, but you will still have this basic set property. So let me explain this. The general case. So there are two properties which are important to make things work. The first one is that if you look at this linguistic character, so I said it was an element of this Grothendieck group. So something, a virtual character but in characteristic 0. Okay? From this group, I can apply the decomposition map, the reduction map, to end up in the Grothendieck group in characteristic L. And if I do this to a character like this is actually the same as first decomposing theta, and then applying the same construction. So it's not exactly the same map, because here it's really for representation in positive characteristic, but it doesn't really matter. This cohomology, you can really change the ring of coefficients. You can, instead of taking the field of characteristic 0, you can replace it by this field of characteristic L, do the same construction, and you will have this equality. Okay, that's the first one. So from this, you can guess that if you're starting with thetas which have the same decomposition, then the decomposition of the linguistic character will be the same. Okay, so modulo L, that means that you cannot separate the RTG theta if theta they have the same restriction on the L prime element, if they have the same decomposition. Okay, so not only you have to group them by series, by geometric conjugacy classes, disparity theta, but you also have to pay attention to the restriction of theta to the L prime part of the torus. Okay, so that's one thing. And the second property, which is kind of dual, which I will use later, is that if you apply not to theta, but I say that for that construction, you have to apply to some irreducible character. But you could do it for any representation. For example, a projective representation. So which one I'm going to take? I'm going to take the block, the regular representation of the block corresponding to theta. So let me do it this way. So I'm looking at the regular representation of TF, and I'm cutting by this block. So it's still a projective representation. It will be here the minimal that you can get, which will contain theta. So you have a projective representation of the torus. You apply this strange construction. It should give you not a representation, but really a character. But the property is that now it's not just any combination of characters, it's a combination of projective characters. So it's a virtual projective character. So I will denote it something like this. So it's in the Grothendieck group of the category, the additive category of projective representation. So by this I mean really if you can express the linguistic character here when you apply to that projective module as a sum and difference of projective representations. Okay, so maybe. Yeah, so maybe let me say a word by this, and this so that actually these two properties will become clear. So we can define. So when you work So in characteristic 0, you work with individual cohomology groups or these cohomology groups. Okay, but in positive characteristic, there is a better way to, and the alternating sum. Okay, and the construction of RTG theta, you can see it as a sum. So now I'm just going to do some sort of tensor construction. So taking the isotypic part is the same as taking the hom of the one-dimensional module corresponding to theta to the cohomology. Okay, that's exactly the same. That's really taking this theta isotypic part. Except that here, since it's a right action, it's probably, I should have taken a tensor product, but that's not very important. In characteristic L, the equivalent of doing such thing is working with, work with not with individual cohomology groups, but rather with a complex. So let's say K. It's a complex of OGF modules such that the cohomology of this complex is really the cohomology that of the variety. And now you can do the same construction, but in a more functorial way. You take any representation, V, and you can look at the hom from that complex, to the representation, from the representation to the complex. Okay, so now it's really a functor in the derived category. So it's something which lives in the bounded derived category of GF modules. Sorry? Yeah, it's okay, yeah. I mean, I could do it over O. I mean, the important thing is actually I could do it over O or over K, and that would be a compatibility. Okay, so the complex over K is really the reduction of the complex over O. That's yeah. And if you do that construction on a functorial level on these derived categories, then you can pass to the Grothendieck group. And why do we really recover the same construction in characteristic 0 is that it's because in the Grothendieck group, if you look at the class of the complex, it's actually the same as looking at the alternating sum of the class of each of his cohomology group, which is the same as the cohomology of the U variety, so the class here. But it's really important to do, this construction because each cohomology group, they can have bad properties with respect to reduction modulo L. For example, if you're working over the ring O, you can have some torsion in the cohomology. So when you extend the scalar to the characteristic 0, that kills the torsion. So that we have some effect when you look at these characters. But then when we reduce modulo L, that torsion, it gives some contribution. Okay, and you see it modulo L, which is bad because you really want something that goes from characteristic 0 to characteristic L. But somehow if you consider the complex, you can pick a nice representative. So the idea.
Another question about these below the section. So previously the cohomology had like bimodule structure, GF on the left and TF on the right. So somehow now you're only looking at one bucket? Like
yeah, I should have said that exactly. So that's TF, yeah. Thank you. Sorry.
Yes.
That's KTF.
Yes, okay.
Yes, thank you. No, you're right. We induce now a structure of bicomplex with both actions, both commuting actions. And the way, I mean, the properties of both of these actions on this variety allow you to take a nice representative. There exists a nice representative. So this complex is just defined up to quasi-isomorphism. So isomorphism in this derived category. There is a nice representative of this one. Let's say over O as a complex which is bounded. So you have only finitely many terms when you write your complex. This is a little bit what I wrote here. And also it has projective terms, and the terms are finitely generated projective modules. Projective as left modules and as right modules. So as OG modules, really, as left OGF modules, and also as right OTF modules. So if you really want to look at both actions at the same time, what will happen is that all the terms, they will have, I mean, you can compute somehow what could be the vertex of the complex, which will be the maximal vertex of all the terms, and it will be something which will be diagonal in OGF and OTF, that you embed diagonally. So that will be the last part of my digression, probably.
So it's really a perfect complex.
It's a perfect complex, both as a complex of GF modules and TF modules.
No, that's a theorem, right?
Yes, that's something general when you look at, if you want to understand the properties of this complex, you have to understand how the groups act on the variety. You have to compute the fixed points, and the main theorem is that there is a representative with permutation modules, and the permutation modules that you have to take are of the form G divided by stabilizers of points. Okay, so as long as you know that the stabilizers of points, there are L prime groups, then it means that your complex is perfect. Okay, so here the stabilizers for the action of GF, they're L prime groups. For the action of TF, they're L prime groups. But if you look at both of the actions at the same time, the stabilizers will be diagonal subgroups of this one. Yes. Maybe I shouldn't say more about this. Sorry, I spent too much time. Yeah, maybe. Sorry, one last thing still. The Rada. So yesterday she defined this functor that was taking fixed point of the group algebra and modding out by all the images of the various traces. So you can do that also not just at the level of group algebras or interior algebras, but also for permutation modules, also for complexes of permutation modules. And there is a way, the nice way with these complexes of varieties, is that if you apply the functor to the cohomology of this variety, it will give you the cohomology of a delinguistic variety for Levy. That there is really, you should really see these varieties not just for the group, but also compatible with all the p-local structure that you have. So the p subgroups, so here the L subgroups, and all the normalizers of these groups. Yes. Okay, but from this, it's pretty clear that you will have these two compatibility properties. All right. Yes, so let me state a theorem. So there was, so for in characteristic 0, the first thing was every irreducible character occurs in some RTG of theta. So here there is a similar statement, is that every projective indecomposable module so KGF module occurs in one of these virtual projective characters. That's the first thing. So that's really this generation statement. And you can actually deduce it really from the characteristic 0. There is an even better statement to this one, which was proven by Bonafé and Rouquier. Is that so again, projective indecomposable module can be constructed from the complexes of the linguistic varieties. So these ones, they're okay when you cut it by the idempotent, so for various t and theta. Okay, so a way to state it is that if you look inside your category of modules, of complexes of modules, the category of complexes of modules, if you look at all these ones and the fixed subcategory that they generate, you get all the complexes of projective modules. Okay, so it's really a stronger statement than just this one. Okay, so just starting with these complexes, you take direct summands, shifts, direct sums, cones of these ones, and you will be able to construct every projective module. So that's very strong. So if you know how to control these complexes and maps between them, there is a way to control all the projective modules. The second one was about the disjointness of the linguistic characters. So here, as I said, you can no longer expect to make the difference between two the linguistic characters for thetas which have the same reduction modulo L. But still, so that's, how should I state this? Yeah, if now you have two characters, chi and chi prime, which occur in different the linguistic characters, and such that chi and chi prime are in the same block, then this forces not just the pair T theta to be conjugate to T prime theta prime, but the pair D with the L reduction of theta to be conjugate to the pair T prime with the L reduction of theta. And that's really the best that you can hope, because as I said, like being modulo L, you can't tell the difference between, the only thing that matters is really this L reduction of this character theta. Okay, so that's really the best that you can hope. So I'm not saying that, all right, let's save a remark for later.
Are they really conjugate or are they in the same relation as?
So this is this geometric conjugacy class. Geometric conjugacy, how should I say? Yeah. So that means that really if you see this one not as a character of, if you see this one as a character of TF, but which is trivial on the L prime, on the L part, then it's a geometric conjugate to this one. So I should say that you can deduce from the original work of Döhling and Lustig. And this was proven by Brouet and Michel, probably in the 90s. And there is a third statement that I want to add, which will be about the basic sets. So these are the two analogs really of what happened in characteristic 0. And the third part, so now I have to assume something on L. So if L is good for G, and L does not divide the order of the component group of the center, then if you look at the sets of, so I will do it like this. So all the irreducible constituents of this RTG of theta, where T varies over the F-stable maximal tori. But now theta is not every character, but a character which has trivial restriction on the set of L elements, that this is a basic set. Okay, and this is really what happened in the case of the torus. That's when you wanted to understand the representation of the torus. I mean, if you wanted just the basic sets, it was enough to consider the characters of the torus, which had trivial restriction on the set of L elements. And here you do the same before applying this Döhling-Lustig construction, and you also get a basic set. Okay.
So kind of like in the first line.
Yeah, sorry, you're right. Thanks. Yeah, my group is assumed to be connected. So otherwise there would be no condition, no extra condition on that. Okay, so really bad things can happen for bad characteristic. And also when you have a center which is too big, for example in SLN, you really have to change the basic set to get something. So there are results. So this is a result by Geck and Hiss. There are further results by Meinhof for classical groups when the characteristic is 2, and that really shows that you have to change your basic set. You can no longer keep this thing. Okay, in one particular case that I should mention before doing an example is that if you look at the unipotent characters, what should I use? This one. Use that one. Because I will actually not look at all the blocks, but only specific ones which will contain unipotent characters. If you look at unipotent blocks, which by definition will be blocks containing at least one unipotent character, okay, so by which I mean some constituents of some RTG of 1. Okay, then the unipotent characters, if that follows from this theorem, they form a basic set for the union of unipotent blocks. Okay, so in all the examples that I will show, and also in the computation that I will make tomorrow, I will always restrict to this case, to the case of unipotent blocks, because they will be parameterized independently from Q. The basic set as well would be much simpler for computation. And when you know how it works for unipotent blocks, there is a hope that you can do the same for other blocks. Okay, there are reduction theorems which are not completely general, but still, the moral is that if you know how to do things for unipotent characters and unipotent blocks, you should be able to obtain information for other blocks. Okay, so let's do an example that I think wasn't in those lectures, but let me use it. So I explained the example of the tori. So what's the next non-trivial example is SL2. Okay, so that will be also a way to explain in that case how this theory of the linguistic works. You'll see. So here, so I have to assume that Q is odd to have something generic. Otherwise, I mean, the classification will depend whether Q is odd or not. Okay, so in SL2, if you want to, so the first thing you want to do when you look at these, the linguistic characters, say look at all these F-stable maximal tori. Okay, so Meinhof said that the number of rational classes of such tori was the same as the number of conjugacy classes of the Weil group. So here the Weil group of SL2 is Z over 2, which means we really have to care about two tori that we call T and T prime. And the first one, I mean, T will be just the diagonal matrices in SL2. So if you look at the fixed point under the standard Frobenius, what you get is just the invertible elements of FQ. And then you have the non-split tori. So I think that he gave the example in GLN on how you can see GL1 of Q to the N inside GLN of Q. So here inside GL2 of Q, you can see FQ square. And when you restrict to SL2, what you obtain is actually like the group of Q plus 1's root of unity. Okay, so here, this has order. This is a cyclic group of order Q minus 1, and this one of order Q plus 1. Okay, so that's these two tori. So if I want to construct the characters of G, I have first to consider characters of these cyclic groups, and then to apply this linguistic construction. Okay, so what about the geometric conjugacy classes? So there is the one that gives the unipotent character. So if you take the trivial of T, Tf, it's actually conjugates to the trivial character of T prime F. Okay, and that's the single conjugacy class. There is one which is similar. So because Q is odd here, there is an element of order 2 here and here. So there is a corresponding character of order 2 that I will denote by minus 1. And it is also conjugate to the same character of order 2 of the other finite group. Okay. Then I will have, for every character of Q minus 1, I will have a conjugacy class like this, where you group together theta and its inverse. So this is for every theta irreducible character of Tf, and I have the same for T prime. So it's important to note here that although T and T prime, they are conjugates for the algebraic group LCL2, they are not conjugate for the finite group SL2, but you can really have the two situations for the pair. Here, T and T prime, they correspond to pairs which will be geometrically conjugate, here also. But if you start with a character whose order is not 1 or 2, so any other character theta of this torus or this torus, then you cannot pass from T to T prime by conjugating a character of Tf to a character of T prime F. That really works only in two cases, this trivial character and this character of order 2. Okay, so what are the linguistic characters corresponding to these pairs? Okay, so for the first one, for the trivial character of the split torus, that's the usual induced representation, and you will get the trivial character of G plus the Steinberg character of G. If you do the one with the split torus, with the non-split torus, sorry, you get almost the same thing, except that you have a minus here. Okay, so you can check that these characters, they're orthogonal if you take the scalar product because of this -1 sign, but that doesn't mean that they have different characters occurring. So that's very important to differentiate these two things. Then if you start with theta, an irreducible character of Tf, which is different for plus or -1, RTG of theta is irreducible. For the same reason, if you do it with T prime, you get a character, an irreducible character, except that you have to change the sign here. So it's now a minus RT prime G of theta. Okay? And the last pair, which is maybe the most complicated one, if you start with this character -1, it will split into two characters of the same dimension that we'll call Chi1 and Chi2. They will be conjugates under GL2 of Q, but not under SL2. And the same thing happened for the twisted torus, except that you have to take now opposite signs. Okay, so all the characters that I wrote here are irreducibles. They're all distinct, except that if you change theta into theta inverse, you get the same here as well. Okay, so let me just write what you get for the unipotent blocks. Yes, so it's when you compute the scalar product of a character within itself. So that wasn't stated completely explicitly in Meinhof's lecture, but he said that if you want to compute the scalar product of two characters, two linguistic characters, so he said it's different, it's always less than the order of the Weil group. But you can actually compute this exactly. This is will be related to, so this way I will not be able to write it. But this is the number, so if you look at the number of elements in GF such that, okay, so the normalizer, so I don't know how to write this. I want to say the number of of elements in GF which conjugates this pair T theta to the pair T prime F theta prime. And I have to mod out by the centralizer of the pair F theta, something like this. Okay, so but you can, if you really look at the description of these characters in terms of elements of the Weil group, it will be just the centralizer of the character theta in the Weil group. Okay, so it's something you can compute explicitly. And the thing is, when you have when you do this computation for these characters, RTG of theta, since here theta and theta inverse are different, okay, and the element of the Weil group, the non-trivial element of the Weil group sends theta to theta inverse, so that will really tell you that the centralizer is smaller, and you'll get a scalar product 1 in that case, whereas here, because this one is actually stable under the action of the Weil group, you get a multiplicity 2 when you compute the scalar product. So you have two irreducible characters. Okay, so let me finish by the unipotent blocks. So if I assume that L does not divide the center of SL2, and there are two cases. So SL2, its order is Q times Q minus 1 times Q plus 1. So I said this before, I should say it again. L never divides Q in the setting that I'm working in. So it either divides Q minus 1 or Q plus 1. It cannot divide both, otherwise it would be equal to 2. And what you get is that if L divides Q minus 1, which is the order of TF, you'll have in the unipotent L block, so you have the unipotent characters, and you also have the RTG of theta, or theta is different from 1, and theta reduces to 1 modulo L. So that's really what was the theorem was saying before. And for the split torus, that's exactly the same. You still get this 1 and Steinberg, which are both, I mean, for the torus T or the torus T prime, they both appear in this Deligne-Lucé character. And then you would add now induction from the torus T prime. So it's a minus here. Okay, and I will finish by the. Sorry, I still want to write the decomposition matrix. So without explaining it, so I was planning to show you other matrices, but I'll do that tomorrow. For SP4 and F4, so you will see what kind of general properties we can expect on these matrices. But here it would not be so clear. So if you look at this decomposition matrix, restricted to unipotent blocks, so you have 1 Steinberg, all the RTG of theta. So when L divides Q minus 1, sorry, you'll get 1, 0, 0, 1, then a 1, 1, 1, 1. Okay, so there are two phenomena here. Well, the trivial character remains irreducible modulo L, of course, but the Steinberg in that case also reduces to something irreducible modulo L. And if you take this Deligne-Lucé character, what happens when you reduce it modulo L? Well, because of the compatibility that I stated before, it's the same as reducing modulo L this one, which by definition is 1. So you just get the RTG of 1. But what is the RTG of 1? Is 1 plus the Steinberg. Okay, so you get, on each row here, you get a 1 plus 1. Now if you do the decomposition when L divides Q plus 1, sorry. So you have a different set of characters. The trivial remains trivial. modulo L. But now the Steinberg splits in two. One copy of the trivial, modulo L, and some other representation, simple. And if you look now at what happens on this one, when theta goes and becomes 1, you have minus RT prime G of 1, which is Steinberg minus the trivial. Okay, and Steinberg minus the trivial, what is it? If you take the difference of the two rows, you get 0, 1, 0, 1, and so on. Okay. And just as a final remark, you can see that here, well, you have the identity matrix. So this is the basic set. This is also a basic set here. You don't have the identity matrix, but it's still something which is unitriangular. Okay, so you cannot expect to conjecture any general phenomenon just based on SL2. So I will show you like bigger matrices to see that this is actually not specific to SL2. I'll stop here. Thanks.
There is this Lustig classification of irreducible characters to 0. Is it possible to say when the two such representations belong to the same block?
So there is a compatibility between the families that Lustig defines and what happens modulo L. I think the best statement that you could hope for is that there is a filtration on the category of representations by families, and if you take the subquotients of this filtration, they are semi-simple. Okay, so that's, you will, I mean, on the examples I will show tomorrow, you will see that on the decomposition matrices, you will have diagonal blocks with respect to these Lustig families. So you can't have any interaction. And the slices should be semi-simple. But then if you really want to describe the block decomposition, I don't think it has anything to do with the families, but you can do it with this Döhling-Lustig induction. You have to induce specific characters from specific levies. So you have to use a parabolic induction. And from that, you can describe explicitly the block decomposition. So already for the unipotent block, you can say something. Okay.